setting of active inference, with a special focus on belief propagation under deep generative models, and a further focus not just upon optimizing outcomes with respect to some cost function, but the importance of reducing uncertainty that I'm referring to in terms of epistemic foraging. So what is self-evidencing? So the argument here is that everything can be regarded as optimizing or extremizing a single quantity. And by everything, I mean more specifically, beliefs cue about latent or hidden states of the world that are generating outcomes or observations here, given me that I will be, in fact, a model of the way that these outcomes are generated by these hidden or latent states. I'm also including not just beliefs about states of the world generating my observations, but also beliefs about how I am soliciting those observations, how I am acting upon the world, how I'm palpating that world. And the argument is that both these beliefs are trying to maximize this quantity here, which is simply the probability of those outcomes given the kind of outcome solicitor that I am. And I'm motivating that from a number of different perspectives, which I'm sure you'll all be familiar with. So, for example, were I to take the logarithm of this probability and to create it into a potential function, then the kind of outcomes that I would expect to encounter are those that define my attracting set, if you like, or the things that I would expect to observe given I am who I am. And therefore they become intrinsically valuable to me in the sense that they are the characteristic outcomes that I will encounter. So if I read this quantity, the log of the probability of outcomes given me as value, then this extremization can be thought of as a statement of the things that underwrite reinforcement learning, things like optimal control theory in engineering, and in economics, expected utility. I've also introduced a lower bound here, free energy functional, of these beliefs, given the outcomes, that plays the role of this value. These quantities here are nice because if I take the negative value, I can now tell another story in terms of information theory. And that's because the negative log probability of some outcome given me is in information theory known as self-information or surprisal, or more simply surprise, which means that maximizing this quantity means I'm minimizing surprisal or surprise, and I can read that as a statement of the principle of mutual maximum mutual information, or the Infermax principle, the principles of minimum redundancy due to Horace Barlow, and indeed the free energy principle, where the free energy refers to this evidence lower bound here. In turn, the average, or the time average path integral of this surprisal is entropy. So that means that maximizing this means that on average, it will look as if I am minimizing the entropy of my exchanges with the world. And of course, that's the holy grail of things like self-organization, synergetics, and laser physics and beyond. And if I was a physiologist, this would just be a statement of homeostasis. It's just keeping those outcomes that matter within viable physiological bounds, the characteristic states that I physiologically would expect to find myself in. And I use the word expectation there because that brings me to the final reading of this quantity, which, if I were a statistician, I would call a model evidence. And now me, M, becomes a model, my model of the way that these outcomes or data, sensory data, are generated. That is also known as the marginal likelihood, or just more simply the evidence, and hence self-evidencing here. And that motivates the story in terms of the Bayesian brain, evidence accumulation, things like predictive coding in engineering and in the neurosciences. So that's the idea. Let me just focus on this, the practical objective function that you would actually use in a machine learning setting, and that many people think may be an apt description for neuronal dynamics as a gradient flow on this objective function. So it is in machine learning an evidence lower bound, and we'll see why that is the case in a second. But first, let me just try and motivate where this comes from. At its simplest, you can probably think of it as an expression of James's maximum entropy principle, where the entropy pertains to the beliefs about the latent states that I cannot observe. So I'm trying to not commit to a very precise belief about the causes of my data under constraints. So what are those constraints? Well, those constraints are provided by what I've labeled here as a negative energy, a potential, that are usually decomposed into a likelihood and a prior. Together they constitute a generative model. The likelihood is simply the probability of some outcomes given their causes, and the prior beliefs about those, Bayesian beliefs I should add, about those causes or those states at any given time. So this formulation has some nice interpretations. So I'm just going to take the same sort of arrangement here, where I'm writing out now the free energy explicitly as a lower bound on the log of the evidence. And it becomes a bound in virtue of the fact that the free energy can be expressed as the evidence, noting that the arguments of this P here do not include S, so we can ignore this. It's just the log evidence minus a quantity that can never be less than 0, and that makes it into a bound by Jensen's inequality. And this construction, I think, is really useful from a number of points of view. First of all, if you're in artificial intelligence or, say, deep learning, and you're worried about explainability and interpretability, then all of those worries are dissolved if you commit to a particular generative model that is necessary to define the evidence, because you know, or this becomes your hypothesis about how these data were generated. Furthermore, you can, using this formulation, appeal to certain kinds of Bayes optimality, and we'll look at that later on, both in terms of Bayesian decision theory, but also optimal Bayesian design, in the sense of, what evidence do I go and get in terms of supplying the most evidence that I am, that I essentially, my model is a good model of the world, and if I am my model, then I exist in that world. This leads, from a technical point of view, that sort of optimal Bayesian design perspective, to the notion, not unrelated to things like David McKay's active learning, that there is the best way to go and get data to explore the world, and that's certainly going to be the focus of this talk. Another way of arranging this equation reveals another very interesting set of interpretations. So all I've done, I've just switched around some of the terms, and it's now written in a way that a statistician might understand this free energy functional. It is a mixture of accuracy and complexity, where the accuracy is just the expected log likelihood under my beliefs about the parameters or the latent states generating my data, with a complexity penalty that is simply the divergence between my posterior beliefs Q and my prior beliefs P. So this scores the degree to which I have to change my mind on seeing some new data. In other words, the degrees of freedom that I'm using up in providing an accurate account of the data at hand. And clearly that's just a statement of Occam's principle that I aspire to, or the best explanations for some observable outcomes are those which are the simplest as possible. From the point of view of computer science, this is also directly the computational cost of a belief update. It's, I repeat, the degree to which I have to change stuff or move my beliefs in some information space or belief space in order to accommodate the new data. And if you're in engineering, this matters literally in terms of the amount of electricity or the amount of energy it costs in order to do that belief updating via the Zielinski equality and Landauer's principle. So we've got the right kind of structure here that has a lot of, if you like, phase or constructability in relation to a number of different perspectives on good behavior and good data sampling. What I want to focus on, though, is what it means to sample something, because that's a very active thing. The data that I get depends upon the moves that I make and the actions that I take and where I look, for example. So essentially, all I'm going to be talking about is, can we use this objective function, this elbow or variation-free energy, as the basis to define what would be the optimal way to act? And to cut a long story short, what we're going to see is that if I can evaluate the free energy consequent upon a move on the world, consequent upon an act or a sequence of acts of policy, then if I can evaluate the expected free energy, I can, in principle, select that action that has the greatest expected free energy, where in the same way we can decompose the evidence into accuracy and complexity, the expected free energy that scores the goodness of an act becomes the expected accuracy and the expected complexity. And the story is going to be that this expected accuracy is effectively the objective function that underwrites optimal Bayesian design, and the expected complexity underwrites optimal Bayesian decisions under some beliefs about the kind of outcomes that I encounter. So that's the story. I usually introduce this account by posing a question to the audience, but as I'm not actually there with you, I'll have to guess what you might have said. So the question is, imagine you're an owl and that you're hungry. So what are you going to do? And I usually pick on the person in the front row, and they say, quite correctly, well, I'm going to look for my food. I'm going to search for my prey. And indeed, this is an owl searching for her prey here. And that answer has, I think, a number of profound implications for the kind of calculus that you might bring to the table to score the goodness of a particular act or policy. And I'm going to deliberately contrast two approaches. You will recognize either one or the other side of the coin that I'm going to present. I'm deliberately introducing a dialectic. I will repair it later and show that one is a special case of the other. But for the moment, I just want to emphasize the differences. And the differences are between the assumption that there exists some value function of the states of the world that would ensue if I were to take this action denoted by u at time t. And if I knew what this value function was and I could work out the consequences of my action, then I could maximize this value function and define an optimal state action policy. And I'm denoting that state action policy as a policy which is a function of any state at any one particular time. However, remember that what you're actually going to do is search. You're going to search for your food. Searching is a euphemism for reducing uncertainty about the location, in this instance, of your prey. Uncertainty is an attribute of a belief about states of the world, which means that in searching, you're not optimizing a function or a value function of the states of the world. You're optimizing a function of beliefs about states of the world. And furthermore, when you're searching for food, it really matters what order you do things in the sense that if I tried to eat my food before I had found it, I would get a very different outcome from first looking for my food and then eating it. So that calls into question a very different kind of policy, which is not a state action policy. It's a policy, a sequential policy that entails a sequence of actions as we roll out into the future, which means that if optimal action is scored by a functional of beliefs, I'm denoting that functional by G, which we'll see in a second is the expected free energy, of beliefs that ensue from a particular action, then sequences of action have to be scored by a path integral or a time integral as I roll out into the future. And I'm using the word path integral deliberately because, of course, from the point of view of a physicist, that's the accumulation of an energy function, which is just an action. So what we can do is we can regard this kind or class of optimization procedures or formulations as committing to Bellman's optimality principle, and you'll be familiar with these in optimal control theory, dynamic programming, deep reinforcement learning, such as utility economics, Bayesian decision theory, and the like. Whereas this class of optimization rests upon Hamilton's principle of stationary action, and the free energy principle is one such example in the context of unpacking that in terms of action and sequential policy optimization. We refer to that as active inference. In neurorobotics, it would be the approach taken by people interested in artificial curiosity and intrinsic motivation. It is the approach taken by people wanting to design the best kind of experiments through the principles of optimum Bayesian design to resolve uncertainty and to quantify uncertainty in an optimal way, leading to sequential policy optimization and partially observed Markov decision processes. So that's what I want to pursue, and the game will be trying to get back to the Bellman optimality principle and ask, well, what would have to be the case to make the Bellman optimality principle conciliant with Hamilton's principle of stationary action. So I've just cartooned here the, if you like, computational architecture that one has in mind from the point of view of these evidence bounds or variation free energies. The outcomes are sampled from the world. They come in, they are used to optimize beliefs about hidden or latent states of the world in terms of this functional, the free energy functional here, in order to provide an accurate account of the outcomes in terms of unobservable states out there, whilst at the same time minimizing complexity. And once we've optimized those beliefs, we can then roll out into the future under plausible policies. And then we can score those in terms of the expected complexity and accuracy, which we'll see on the next slide, basically corresponds to minimizing or choosing those policies or the actions implied by each policy that minimize risk and ambiguity. So just in a bit more formal detail, again, you don't really need to understand the maths if you're not familiar with it, but there's a beautiful symmetry here between the objective function for good inference in the moment and the objective functions for what I should do next in terms of the expected outcomes or the expected, in this instance, free energy. So I've just written down the free energy in its two forms just by swapping the order here, just to reveal or evince the decomposition into accuracy and complexity. And as we just rehearsed, noting that this functional is a bound on the log evidence, which is the thing that we want to maximize. And all I've done here is now take the expectation of this under technically the posterior predictive density over the outcomes that would happen if I took this policy pi here. So this is just this quantity, but expected under the most likely outcomes, given my beliefs. And you can see immediately that the functional form is preserved exactly with the exception of conditioning upon a policy. So the expected complexity now becomes risk, and the expected accuracy becomes ambiguity. The expected bound becomes something I've called an intrinsic value, and the expected accuracy, log evidence now becomes an extrinsic value. So what do I mean by those? Well, let's just go through bit by bit what these things mean. First of all, let's simplify things by assuming I have no preferences. I have no prior beliefs about the kind of outcomes that I expect to sample. So that just leaves me with these terms here, the expected bound. But because now I'm taking an expectation over observations in the future, these outcomes now become random variables. And now what I'm trying to do is to maximize this KL divergence. And what is that KL divergence? Well, in the visual search literature, it would be known as an expected Bayesian surprise. It's essentially the difference between my beliefs about states of the world that are unobserved, given some future outcomes under a given policy, relative to those beliefs without those outcomes. So it scores the relative entropy or the information gain afforded by those outcomes that I would get under that policy pi. And for those people who know information theory, you will recognize this immediately as very simply the mutual information between causes S, states of the world, and outcomes O that are observed under a particular policy pi. So we're trying to maximize the mutual information between stuff that can and cannot be seen. Let me now take focus on risk by removing ambiguity from the game. So what is ambiguity? Well, it's just the uncertainty about the outcomes given their causes or the states here. So let's imagine, as is often imagined in many aspects of machine learning, that I can see directly all the hidden states of the world. So there's no ambiguity in my observations in relation to the causes of those observations, which means that basically the O's become the S's and this term disappears, just leaving us with this term here. So what's this term here? Well, it's just the difference between what I think will happen, either in terms of states or outcomes, because they're effectively now the same, relative to what I preferred would happen. So it scores the difference between the anticipated or expected outcomes if I pursue this policy and what I would actually prefer or expect to happen. So in that sense, it becomes risk, and indeed it's this kind of functional can be found in economics in the under the rubric of risk-sensitive control. In engineering, this is KL control, minimizing the distance between, my apologies, the divergence between controlled outcomes and a priori preferred outcomes. So what I'm going to do now is take the last kind of uncertainty off the table, which is that due to the risk inherent in the intrinsic value. So now it doesn't really matter. So I'm assuming that there's no uncertainty. If I commit to this action, then the outcomes are effectively known, and that just now leaves the expected value that we entertained in the first slide. So notice what we've done here. By taking successive sorts of uncertainty off the table, we've now got back from a generic formulation in terms of risk and ambiguity or intrinsic and extrinsic value. We've now got back to the thing that the Bellman optimality principle would pertain to, simply optimizing an expected value or a function of the outcomes that ensue from certain states. So this is the repair of the Bellman optimality principle and the Hamilton's principle of stationary action. But in repairing that, we've had to ignore lots of sources of uncertainty. And so in summary, what we have is a notion of Bayes optimal behavior that has, in its most general form, two bits to it. And I've cartooned that here in terms of optimizing an expected free energy, extremizing or choosing policies pi that give you, that extremize the free energy, which is just maximizing this mutual information or this information gain here in the future, whilst at the same time maximizing my expected value defined in terms of my prior preferences. And this can be read basically as a combination of making Bayes optimal decisions in terms of policies I pursue and Bayes optimal design in terms of soliciting the right kind of data, which together comprise active inference operation defined through the extremization of this expected free energy. So what I'm going to do now is try and unpack that with a simple example, and then turn to a slightly more complicated example, which I think is interesting and highlights the importance of both that intrinsic value, that's sort of the thing that underwrites the artificial curiosity or the exploration, and at the same time appeals to how far you can get when you consider sophisticated or deep generative models of the world. But let's start off simply. So I've made a big thing about generative models underwriting all this. That you have to have a generative model before you can evaluate the free energy. You have to have a free energy before you can evaluate the expected free energy. So what kind of generative models do people normally use in choice behavior or decision making? Usually people use Markov decision processes. So here's a simple rendition of a Markov decision process, but is now equipped with this universal objective function here, the expected free energy. So how does this work? Well, it's very simple. We've just got different states of the world that can generate observable outcomes, and that probabilistic mapping is denoted by a likelihood mapping, usually in our work, a tensor or matrix A. And then these states of the world change over discrete time steps to other states of the world via a probability transition matrix, which we usually denote by B. But crucially, those probability transitions, those ways in which the world changes, for example, where my eyes are pointing, or the motion of an object in the visual scene, some of them depend upon the policies that I commit to. And the policies in turn are sampled from or determined by the expected free energy. So that's why we've got this slightly augmented MDP, or partially observable Markov decision process here. Ignore the equations, they're just defining the functional form and the probability distributions for this graphical model. The reason I'm showing the graphical model in this format is that there's a nice conjugate or sister kind of graphical model known as a normal style factor graph or Forney style factor graph, which tells me immediately if I can write down one of these, then I can write down one of these. And if I can write down one of these, I can simply and very quickly read off the requisite message passing between different nodes over edges that would allow me to invert this model given some observations. And by inverting, I simply mean mapping from the consequences back to the causes. So the forward model, the generative model, can be regarded as a forward mapping from cause to consequence, and then the inversion mediated by these message passing passes here corresponds to the inversion, getting the causes from the consequences. And if I just take off-the-shelf belief update equations from this kind of factor graph, for those people who are interested, there's a curious twist here that the random variables now, or at least the sufficient statistics of random variables in this graphical model, are now assigned to the edges and the messages passed along those edges, whereas the nodes now become the factors in my probabilistic graphical model, hence factor graph. But the key thing from our point of view is that there is off-the-shelf math to work out the message passing for any given graphical model. So if I can write down the generative model, I can always simulate belief updating, active inference under that generative model. Interesting from the point of view of neuroscience and psychology, this message passing looks remarkably similar to what the brain is doing. So remember, all we're trying to do is get the best beliefs about what we don't know. So what don't we know? Well, we don't know the hidden state of the world, S, in the past or in the future under different policies pi, and we don't know the policies pi that we might pursue in the future. And I've actually equipped this probability density here with a precision parameter beta. But the key things we don't know are basically the states and what we're doing. We also don't know the parameters of the likelihood and the initial states D and the transition matrices B. So we have to update those. So just looking at those off-the-shelf message passing or belief update, belief propagation or solutions to the belief propagation, you can see that the expected state of the world under a given policy is a nonlinear function of a linear mixtures of outcomes and beliefs or expectations about the past and the future that has the functional form very much like we'd use in discrete updates in neural networks with neuronal networks with a sort of voltage current activation function applied to some connectivity matrix, pooling together various expectations or activities, neural activities. The policy selection is just a standard softmax response function where the value of policy is given in this instance by a precision or inverse temperature weighted free energy functional that plays a role of the, if you like, the value of that particular, the goodness of that policy. And interestingly, the temperature parameter itself can be updated and looks very much like a reward prediction error. That's another story. The learning is really, really trivial and looks very much like associative plasticity or Hebbian plasticity in the sense that you're just accumulating coincidences or occurrences technically as Dirichlet counts or concentration parameters in exactly the same way that people write down associative plasticity rules in the brain with an associative and a decay term here. And then action, you just sample the action from the most likely policy or the policy that has the greatest expectation. So that's the mechanics and the scheme that we use. It has a degree of biological plausibility, but I think from your perspective, that's less interesting. More interesting is how does it behave? So I'm now going to illustrate that using a very simple, as simple as we could get it, two-step task that involves very much reducing uncertainty and searching for food, or in this instance, a little red reward here. So this is a game. So this little mouse can make two moves in a T-maze, and it prefers to be sitting with its reward. So it doesn't know if the reward is on the right or the left. So it could take a gamble, and I should say that if it commits to one arm or the other, it has to stay there. These are absorbing states. So it could take a gamble and either be with its reward for two moves or not for two moves. But this paradigm, in this paradigm, the mouse has another option. There's an instructional cue at the bottom, at the lower arm here, that tells it definitively, or at least probabilistically, where the reward is. So it's now got the choice of wasting one of its moves that it could have spent with the reward, were it to find the reward, by going and getting the instructional cue and then going directly to the reward. So the expected utility is exactly the same for the two policies, but clearly the uncertainty reduction and the information gain afforded by the instructional cue should make this policy going to look at the instruction, the sign, and then exploit that knowledge by going to secure the reward, should make it much more appealing and have much greater affordance. These are just the specification of this generative model in terms of the probability transition matrices and the likelihood mapping here, and here are the prior preferences that basically mean that this animal just prefers to be sitting on her reward. It doesn't matter whether it's on the left or the right hand side. So very simple to write down, very simple to iterate and integrate and look at the ensuing behavior. This is an illustration of behavior where I've now marked the initial states, whether the reward was on the left or the right here, with the colored circles here. The posterior density or distribution over the various policies. Do I stay and then move down? Do I stay and move down? Do I stay and move down? Do I go to the right arm and stay there? Do I go to the left arm and stay there? Do I go down and then go to the right arm? All the different policies it could entertain. It evaluates in terms of the expected free energy as we have described, and then samples an action from that. And then the trial repeats for 32 trials here. And here are the outcomes in terms of reaction times, in compute time, and the expected value of the different actions here. I've also shown the parameters of the initial states, the context of each of these trials here. Is the reward likely to be on the right-hand side or the left-hand side? And I've done that because I played a trick on this animal, I have, after the first couple of moves, always left the reward on the left-hand side. So that as time progresses, there is the opportunity for this self-evidencing creature to accumulate knowledge about the contingencies and the consequences of action. And I've done that to illustrate a very generic kind of evolution of behavior as things become more familiar with their environment and move from a mandated exploration to an exploitation. So as anticipated in the first few trials, this policy is basically go and look at the queue and then go to the left-hand side, because we know where, well, the mouse knows where the reward is. But as time goes on, there is less and less epistemic affordance or information gain afforded by this instructional cue or conditioned stimulus here. And that's because the mouse knows that the reward is always going to be, or more likely to be, on this side. And at some point, the intrinsic value falls below the extrinsic value of going directly to get the reward and staying there for 2 moves. And that's what we see here. We see this discrete transition from exploratory to exploitative behavior, simply because there is no more information gain or epistemic affordance from doing any exploration. And then deterministically, we move to an exploitative behavior where we go and sit on our reward and stay there for the 2 trials. So that's the basic behavior. I'm now going to close by giving you another example of exactly that kind of epistemic behavior, but using a slightly more sophisticated generative model of the kind that you might use for language understanding, or in this instance, reading, where there are no preferences. The only thing driving behavior, an active sampling of the sensorium, is the desire to resolve uncertainty. The reason becomes, if you like, slightly more sophisticated, is that we're going to be using a deep generative model, and a deep generative model with a twist. So here is the same graphical illustration of the generative model that we've just been using in its graphical form, probabilistic graphical form, and the accompanying factor graph. And all we're going to do is take one of these MDP structures and put one on top of the other. But the twist is I'm going to do it with a separation of temporal scales, and hence this diachronic here. What does that mean? Well, what I'm going to assume is that most worlds evolve at multiple temporal scales, and the fastest scales are always contextualized by some state transitions of a contextual nature at the level above, and then some more contextual states are contextualize those contexts with an even slower time scale. So how would you write that down in terms of the graphical model? Well, you just have a slow Markov decision process with transitions from one state to the next over an extended period of time, which is extended simply because this provides an initial context for a fast unfolding of states at the lower level that are actually generating the sampled observations. So from the point of view of the generative model, what we're seeing here is a slow fluctuation in some abstract contextual state that provides the initial priors, if you like, empirical priors or constraints on the starting point for a fast trajectory during one cycle of the higher state. From the point of view of the factor graph and the message passing, what that means is that, if you were to put this generative model into that belief propagation or variational message passing scheme, what you would see is it would look as if the agent or the belief updating is accumulating evidence at a very fast scale for the context that is a best explanation for the evidence secured or accumulated very, very quickly. And then you'd have a slow accumulation of evidence for an inference about the context in which you're operating. Technically, what we're doing here is basically destroying the Markovian aspect of a Markov decision process and rendering it semi-Markovian by introducing this separation of temporal timescales, which incidentally introduces all sorts of interesting issues about the scheduling of compute times and from the point of view the computation. So here's the example. I'm going to use an example of reading, but made very, very simple, and using not letters, but little visual icons. So this is basically what this agent can see. She can basically foveate certain letters, pile of seeds, a cat and a bird. And she also has access to where, which letter that she's actually looking at. So what would I need? What hidden latent states would I need to generate these kinds of icons? Well, first of all, I'm going to need to know what letters are available to look at and where I'm actually looking. So if I knew, for example, that there was the word feed that has these two letters, bird and seed, and I knew where I was looking at this word, then I could generate exactly the thing that would be observed by foveating on that letter. So all I need to know is the what and the where. Basically, what's the scene I'm looking at, and where am I sampling that scene to generate a visual outcome. I've introduced here, just for fun, a font change by flipping these iconographic words around the horizontal and vertical axes. So that would be an apt generative model, just to generate outcomes, and I could put probability transition matrices in terms of the different words that I might be sampling. What would they come from? Well, they would come from a deeper context. They would come from the sentence that I was reading, and the particular word that I would need to generate in order to generate the letter, to generate the outcome, would depend upon where in the sentence, which word was I looking at, and what was the sentence. So again, we have this what and where, separate hidden state factors determining the context, which determines the quicker unfolding succession of outcomes or observed outcomes that depend upon where I look. So here I've just got 6 different contexts, or 6 different sentences: flee, wait, feed, wait, a succession of these words here that ensue, and I can sample by looking at the different words within the sentence, in terms of selecting the right policies, in terms of jumping to the next word, having foraged around the current word. So when we integrate that scheme, or we solve those belief update equations, this is a kind of behavior that you see. So effectively we're trying to reproduce natural reading behavior. And what we see at the top is the sentence actually shown to the synthetic subject with the 4 words, each with two letters in it. And these are her saccadic eye movements that she chooses through this process of active inference or self-evidencing to resolve uncertainty, to infer not only what am I looking at, but what is the context in which she has been looking at things, namely building beliefs about the sentence or the context at hand. This is a movie rendition of the posterior beliefs that reflect that evidence accumulation in terms of the first and the second level inferences. Basically, what letter am I looking at, or is she looking at, and what is the sentence. And the crucial thing that I wanted to illustrate with this simulation is that the way in which information is sampled is very, very akin to the way that you and I would actually sample our visual world, for example, in the sense that we don't hang around when there's no more information to secure from looking there, and we jump to the most informative location. So notice, as soon as she sees a cat, she knows exactly what the word has to be, because a cat can only appear in the word flee. So there's no epistemic affordance in staying on this letter. She jumps immediately to the next letter. The first outcome, the first location she chooses to look is a bit ambiguous. There's nothing there. That could be a couple of things. So she just checks by looking down here to resolve uncertainty introduced by the font inversion, and correctly concludes that this is a weight output, a weight word, and then jumps to the next. A bit of ambiguity. There's a bird, it could be one of two things. So she checks, and as soon as she's resolved her uncertainty, goes to the final outcome. So, to my mind, a compelling illustration of how to most efficiently design your sensory experiments to resolve uncertainty about your hypothesis. So this is effectively what a scientist does in terms of designing experiments. But in this context, it is just simply making sense of sensory data. These are the same results, but using a very different display format. What I've done here is show or color code expectations about hidden states of the world at the first and the second or deeper level here. So remember, these expectations, what's the word in play? Going to be one of three, so these all sum to one. What's the sentence in play? Could be in 1 of 6, and these all sum to 1. So as the synthetic agent accumulates by reading the text, she is able to very confidently infer that the first letter is flee, moves to the next letter, that is wait, moves to the next letter, feed, and slowly accumulate beliefs about the sentence that is generating this particular actively sampled sequence of outcomes. And because sentences 1 and 4 share the first 3 words, she has to wait right till the end before she can resolve uncertainty about the final sentence. This kind of belief updating is very reminiscent again of what you see empirically. So if you actually look in the brain using sort of invasive electrophysiology, you can imagine that the unit activity here recorded during the delay period, pre-saccadic delay period in the prefrontal cortex, you can imagine that it looks very much like this synthetic belief updating, where neural activity or spiking is representing the most likely or the expected hidden state at a high level of a generative model. If I were to take these time series here and then just filter them using the frequencies that people use in EEG research, then I get these fluctuations in synthetic local field potentials, which again look remarkably similar in many details to those observed empirically in earlier and later visual cortex during or while measuring perisaccadic field potentials during active vision. Their similarity, some aspects of this are very interesting from the point of view of the belief updating and the sort of the compute, in the sense that a slow accumulation of evidence at the highest scale translates into slightly lower, slower frequencies in terms of belief updating that is seen both in terms of the simulations, but also in terms of the empirical signatures or neuron correlates of this kind of belief updating. So that's it. I'll stop there just by reminding myself and everybody else that all of this ensues either in the moment or in expectation consequent upon an action, on an appreciation that evidence, if you like, the evidence that exists, the most important existential objective function, can always be decomposed into simplicity and accuracy. Thereby, everything that I think and do should be basically trying to provide an accurate account, but as simply as possible. And with that, it only remains for me to thank those people whose ideas I've been talking about, and of course to thank you for your attention. Thank you very much indeed.
Okay, thank you, Karl. Great, that's fascinating stuff. And you have time for questions. I seem to be getting some echo here, but I think that the way we can do this is people can either just pipe up with a question or can type something in the chat. So while we're waiting for some questions to come in, I will go ahead and ask one of my own then. You sort of briefly skipped over the sort of connections to the neuroscience. And I do know there's some number of neuroscientists on this listening to the lecture. So I wonder if you could just give us a brief sort of view of that connection, and why is this these Bayesian models thought to be somehow, or how accurately do they come to modeling what's really going on in the human brain? Does that make sense?
Excellent question. Yeah, I deliberately took out the neurophysiology for time, but also to just emphasize the computer science part of it. But that the biological plausibility and using this as an observation model of neuronal dynamics and associative plasticity is an important motivation for this work. And specifically, how that could go wrong in certain conditions, say like schizophrenia or depression. So it's a really important question. The brief answer is everybody, including me, has been very impressed by how similar the functional forms of the updates are in when just deriving the updates from a first principle account of the sort that I've given you. And those neuronal dynamics and connectivity weight update equations that have been used in computational neuroscience and to model electrophysiology, remarkably similar at a coarse grain level of analysis. Further to that, perhaps one instance of that is the kind of message passing you get when you deal with generative models with continuous time and continuous state spaces. So when you implement this sort of model inversion for those continuous time and state models, what you get out is a Bayesian filter, which from the point of view of an engineer or a neuroscientist would be known as predictive coding. So predictive coding is the special case of this kind of Bayesian mechanics on a generative model that deals with continuous states and time of the sort you might want to use for early vision or very early acoustic processing, for example. And there's a lot of biological plausibility that attends writing down the dynamics implicit in the Bayesian filter or a predictive coding scheme and neuronal dynamics. It's basically a fast gradient flow on a free energy or an evidence layer bound or a marginal likelihood bound. Technically, for those people interested, it is always the case that you can express the gradients of that variational free energy functional as a prediction error. It can either look like a classical prediction error in terms of the arithmetic difference between my sensory data and my predictions of those data, or it can be the same kind of arithmetic difference, but read now as a KR divergence in terms of differences between non-probabilities. In both instances, you can always write down these dynamics, this gradient flow, as a gradient flow on a prediction error. So you can always express these schemes in terms of minimizing prediction error. And I'm emphasizing the predictive coding is to contrast it with another kind of belief updating you get when you don't use continuous state space models, but you use discrete state space models and discrete updates in time. You get a very different kind of message passing scheme, the same maths, and you still use a gradient flow or a gradient descent on the negative free energy or the prediction errors inherent in that negative free energy. So you still get a very plausible account of neuronal dynamics, but it now has this saltatory or episodic nature. Usually every 250 milliseconds, you have these dynamics, and then you supply new data, and then you do gradient descent to get to the next fixed point, which is the solutions that I showed you with that brief propagation before. The next bit of data comes along, you do your gradient descent. And when you integrate those schemes, I notice that it's important that there's a dynamics and a gradient descent that is, if you like, scheduled, usually every 250 milliseconds. What you get from that is our data that look very much like what we see in neuroscience, that implicitly have things like theta gamma coupling, because the every 250 milliseconds is a theta rhythm, and then the fast gradient descents give you faster frequency sequences. You can reproduce all sorts of things using that little two-maze rat or mouse demo I gave you. You can find place cells, you can find, you can simulate mismatch negativities, you can simulate heavy plasticity, you can simulate theta gamma coupling. All of that good stuff just falls out for free from this belief updating under a discrete generative model. So technically, the way that you would actually use belief propagation to solve this in the brain, you'd use variational message passing and formulated in continuous time, so that now it looks like a dynamics, a gradient flow. And that, from my point of view, having done neuroscience and the computational aspects, I have to say that the discrete bits look more like real empirical data than the continuous bits. But it's more than likely the brain uses both kinds of message passing. So the point it has to interface with continuous things like motion or fluctuations, frequency glides, and sound processing, it's likely that that's all amortized predictive coding or Bayesian filtering. And then when you get deeper into the hierarchy, you start to have a quantized or discrete representation that, like grandmother cells and discrete notions, I am in the kitchen, as opposed to being X, Y, Z in relation to some reference or landmark point. At that point, then the better explanation for empirical, both in terms of the computational architecture, the hierarchical architecture, but also the dynamics, seems to be a discrete state-space model with this sort of discretized updates every 250 milliseconds. That corresponds to whenever I articulate a phoneme, or when the frequency with which I palpate my visual scene. If I was a mouse, the frequency which I'm whisking. So most of this sort of discretized sampling of the world seems to appear at about 4 hertz.
Okay. Karl, can your microphone, I think, has we're getting a lot of static on the line. I wonder if you could just try muting and unmuting, if that might help us. I don't know. It may be coming from somewhere else. So we do have another question. So Christoph, do you want to ask your question directly, or do you want me, you can go ahead and just ask Karl your question directly if you'd like. Or I can read it. So he's saying, okay, we have a question about type 1 processes. So it reads, you have focused on type 1 processes in the dual process theory style. I wonder how these principles can be applied to a more holistic model that integrates type 1 and 2 processing. So I think this is related to what we were just talking about, I guess, how high up does this continue to go? Can we get this kind of type 2 or deliberative processing working in these kinds of models?
Has my static gone away?
Yeah, it's gone away. Yeah, thank you.
I shall come close to the microphone. I'd like to say that's a great question. I'm afraid I'm so little what a type 1 and type 2 is. So quickly tell me what they are, and then I'll attempt to answer them.
I guess okay. I'm gonna unmute myself. Yeah, this is just referring to this idea that there's the sort of unconscious fast processes versus the systemized dual process theory, basically. And you kind of were talking about that the higher levels you have more and more kind of discrete processing. Yeah. I kind of wonder how some of these models might explain for how you acquire sort of the higher level knowledge, or how you decide to allocate, I don't know, mental capacity for the sequential type 2 processes, right?
Right. So I think I understand that. Well, I think just as has already intimated that this separation, I think, corresponds to whether you're at low levels of active inference, which can be read as planning as inference. So in machine learning, planning as inference basically means that choosing what to do next is an inference problem, and then I apply all the normal
inference machinery to that and then choose the best thing. So that's effectively one way of looking at planning as inference. So if you had a very shallow model, a lot of that can be automized. Technically, people like to talk about amortization, but we can regard that as sort of habitizing something that was previously deliberatively inferred by having a slightly higher hierarchical model. So if you want to simulate this distinction, what generally happens is, and it might be slightly counterintuitive, but generally what happens is that the fast automatic, which I presume is a type 1, but please forgive me if I got this wrong way around, the type 1 processing inherits from, first of all, engaging in more deliberative planning, in explicit goal-directed behavior. So put very simply, what we do is, say with that simulation of the mouse in the two-step maze, we would it would basically, and we kept the two rewards randomly allocated to the two arms. Then what would happen is that she would, or the simulated mouse would pursue this very deliberative, explorative, planned behavior. She's going through explicitly a sequence of policies and always identifying this epistemic policy, this explorative policy, plan, as you can read policy for plan, as the best thing to do. So that would be, if you like, a minimal version of planned motivated behavior, where the key thing is you are choosing among a number of different counterfactual policies. After a period of time, though, that epistemic policy can itself now become habitized, or if it's the case that the context does not change and the reward is always found on one side or the other side, then what emerges, as we saw in the simulations, is that the uncertainty about which of these counterfactual plans to evaluate and then commit to resolves. So ultimately, there's a priori just one plan, at which point there is no more planning, and you can immediately commit to that particular policy, which effectively now becomes automatized or habitized, and you no longer have any, if you like, volition. Not that these simulations have any volition, but there's no choice at hand. You just do this. Now, notice what happens is, if now the environment changes, and you've a priori now assumed that the environment doesn't change, but you've got these habits, it's very difficult to actually get back from the habit to the active inference with unless you relax your priors over the plans at hand. So it speaks to all sorts of interesting issues about why devaluation, for example, is a natural and emergent property of this sort of hierarchical inference that can become habitized with sufficient exposure to a non-volatile environment. Was that the kind of difference between type 1 and type 2 that you had in mind?
Yeah, that makes sense. It was just flipped in a sense, but and I guess the question is, like, what type of representations you need at the higher level of your MDP hierarchy versus lower, where, for example, I guess at the higher level you have to think about your information source and how do I I guess explore information sources, or that I take into account this possibility. It's probably it's a different type of knowledge that's exploited there versus at the habitual level. Yeah, but
yeah, well, absolutely, yeah. So as soon as you habitize or automatically, or your priors get sufficiently precise that they dominate all the other bits of the expected free energy, by definition, that those epistemic imperatives or those epistemic aspects are suppressed. So, or by construction in this formulation, that's absolutely right. That you have learned that there is no value in intrinsic value in going to find out any more information about this, and you just go, you just do the right thing. So I think that phenomena you'd see at all at all levels of planning. I guess your point is that you clearly have to have a sufficiently deep and sophisticated generative model to actually entertain a non-trivial number of policies, all of which will be scored in terms of what will I learn
how much information would I get if I did that, and is that worth the payoff that comes from the prior preferences or the more utilitarian extrinsic value part of it. So all of this does depend upon a sufficiently deep generative model. The equivalent, I don't know if you're interested in sort of this dual process theory as it relates to physiology, but the equivalent in physiology has been written very artfully by Giovanni Pizzulo in terms of the distinction, and people like Klaus Stefan, in the distinction between allostasis and homeostasis. So instead of worrying about sort of motor choice behavior, you just think about autonomic behavior, interoceptive inference. Then the distinction I think you're talking about is whether you have an immediate homeostatic response, or whether you go and search out for the context, the optimal context that enables the homeostasis. So instead of releasing insulin because my blood sugar is low, I might suspend that automatic response and then go and prepare some food to eat, so that I don't need to release my insulin. So that theme of putting context upon context upon context with deep generative models, I think you'll find is endemic and has to be, in the sense that it's a key attribute of these generative models, and the generative models underlies all the Bayesian mechanics and the behaviors that they're trying to explain.
Thank you.
Okay, we have another question here. I'm going to just read it. There's Arti Malhotra asking about the dark room problem, but I'm going to suggest we save that for the student meeting, unless you want to address that, Karl. But there's another question here on the role of long-term memory on policy selection. Maybe you can just asking for your thoughts on the role of long-term memory on policy selection. But she's also asking about the dark room problem. So if you want to explain what that is and then try to get into that in 10 minutes, we can do that here, or we could save it for the student meeting.
Well, we'll briefly resolve it in 1 minute and then turn to the other question, then we can revisit it at the student meeting. So the dark room problem is the notion that if I want to minimize my surprise, I should go into a very dark room and stay there forever, because I know exactly what's going to happen to me. And on the surface of it, it seems very plausible as a consequence of minimizing surprise. But it just doesn't work. It's one of these false thought experiments. And indeed, you can see that immediately in relation to what we're just talking about in terms of resolving uncertainty. So the first thing that I do when I go into a dark room is switch on the light. Why? Because that resolves my uncertainty about what is causing what's in that room. I think probably more tellingly, the dark room problem just fails to account for action. The dark room problem is only good for sessile creatures or computers that don't have to decide which data to gather. As soon as you move into an active frame of reference, and think about the dynamics of what the consequences of what I'm going to do, then you have to work out what's going to lead to the least expected surprise. And mathematically expected surprise is uncertainty. So it's always those moves that reduce uncertainty. And the first thing I do in a dark room is to switch the light on.
Yeah, I think I've heard you say before that the creature that you would find happily living without surprise in the dark room would be a very different creature than a human being.
Yeah, and they exist, don't they? They're troglodytes. I mean, the large creatures are not surprised by not being surprised by bright things. But I'm sure they have other wonderful sensory modalities to predict and be surprised about.
Okay, so Arti, your second question was about the role of long-term memory on policy selection. So, do you have thoughts on that?
Oh, sorry, right. I was accentuating. Yeah, yes. So, long-term memory. So, again, I'm always referring to the simulations, because I find that to understand the mechanics of this, it's much simpler to dismiss your intuitions and just see what these things do when you put them in play. And it is certainly the case you can get some fundamental changes in behavior through the belief updating applied to the parameters of the generative model. So the example in that two-step maze task was basically accumulating beliefs effectively in connection strengths about the context, so that what you could regard that as encoding is a long-term memory that in the past half hour, from the point of view of the mouse, I'm remembering that the reward is largely on the left-hand side, and I'm slowly learning and I'm remembering that. Now the question becomes, so in a coarse-grained and simple sense, that for me would be the long-term memory, but at what temporal scale? So now you start to think, well, what would happen now if, yes, I left the reward on the left for 32 moves and then moved it to the right? You know, how quickly would it relearn? And of course, if it's accumulated all these beliefs and, you know, technically Dirichlet parameters, physiologically a really consolidated connection strength between the sort of, you know, the populations of pre and postsynaptic specializations, it's going to take a long time for it to reverse its belief in the context of a volatile environment. So then you get this higher time scale that now has to optimize the impressionability of this long-term memory. So to the extent that, this is really procedural memory I'm talking about here, that has to be now contextualized. You get to really interesting games about then, well, what kind of slow generative model, Markov decision process, if you like, would you have to have in order to model a volatile environment, or simply moving from one environment to another environment at a particular time scale. So the really interesting issues, and fairly straightforward issues that have a base optimal and technical solution when it comes to procedural memory. Episodic memory is much more interesting. It speaks to the notion that you've actually got a hypothesis entailed in your generative model that I have been here before, which means you have to recognize in order to recognize I have been here before, either overtly or covertly, then you need to have a representation of I have been here before. And to recognize it covertly as the best expression of what's going on, you have to actually remove all the sensory evidence. So you have to be sort of in a mind-wandering state or a sleep state. Technically, you just turn down the precision and the likelihood of mappings to make it into an agent who is more mindful, not mindful. I use that word and I shouldn't, because it's not mindfulness. It's the opposite of mindfulness. It's, you know, you're actually generating fantasies. So I think the notion of episodic memory is much more delicate and has yet to be properly simulated. I have a colleague, Laura Convertino, who's very interested in doing this, and a number of other colleagues working with. Well, Laura works with Neil Burgess, but in principle you can do it, but you do need a high level, and because of this complexity constraint, it has to be coarse-grained continuously in an optimal way. So you've got to forget all the instances of I've been here before, where here now does not stand in for this particular event, but this kind of event, this canonical or platonic kind of event or narrative. So you have to forget the details optimally, but retain what can be conserved when you next come across this kind of event and say, oh, I've been here before, and when that happened, I did this. And then that becomes literally instrumental in your planning as inference or your active inference. And then you can sort of plan, well, if I go to that corner of the room, or I push that button, even though I've never used this kind of keyboard before, or this iPhone before, my memory of these kinds of things, the last time I did it, then this happened. Then you start to have, again, in a minimal sense, a formalism that might account for some aspects of episodic memory. And these have to be learned, so they can only be instantiated through repeated experience, through accumulation of these Dirichlet parameters, or the learning the likelihood and the priors implicit in these probability transition matrices, the things that underlie the narratives.
Thank you.
Okay, we only have a minute left, so there is one more question here in the chat, which I'll just try and summarize. A question that has to do with the match between, you mentioned a few times that the empirical observations are similar to the simulations that you see, and the question is about how do you measure that similarity. So for example, if you're talking about words that are being learned, then how can we actually find evidence for that by looking at the brain? I mean, can we actually measure those words in some sense? Is that, I hope I'm reading that question right, Nick.
Well, if you read it right, it was an excellent question. So at the moment, what people tend to do when trying to bring together these hypothetical architectures by committing to a specific generative model and then applying standard belief updating schemes, bring that together with empirical, usually electrophysiology. They go for certain characteristic responses that have survived peer review in the literature for at least 2 decades. So I'm talking about things like mismatch negativities or P300s, for example, in EEG research. So what you're trying to do is to demonstrate that these, again, canonical or platonic electrophysiological phenomena are emergent properties of your Bayes optimal scheme. And in fact, interestingly, I didn't show, and I'm now regretting not doing the sort of neurobiology side of this presentation, but that last illustration using that deep model of iconic reading was designed in order to elicit both mismatch negativity and P300 and N400 responses, in the sense that we had the hypothesis that these would be emergent properties of any inference machine that had a deep diachronic structure. More specifically, that surprising outcomes, which we did by changing the font, would only be registered at the lower level, whereas a change in the context by changing the semantics that was violating beliefs at the higher level about the sentence I'm reading, that provides a prediction about or expectation about the next word, would account for both the hierarchical level, where you find things like the P300, P3B specifically, and the mismatch negativity, and in time, in terms of peristimulus time. And indeed, you know, it was what came out of the simulations was almost exactly what you see empirically, that you got this sort of fast surprise prediction error-like response at the lower level of the hierarchy, and you got this more protracted contextual or revision of context, that you would beliefs about context at the higher level of the sort that people normally associate with the P3, at least the posterior parts of the P3. So that would be one example. Ultimately, I think the best way to do it, though, is just to have your in silico brain and a real brain doing exactly the same task. And then under ideal Bayesian assumptions, you can just use the active inference scheme to simulate the belief updating in real time with exactly the same inputs and outputs as the subject, and then just look for correlations between the two. So, you know, in principle, that would be much more, if you like, that would be a more formal way to test the hypothesis that this hypothesis about the belief updating scheme is apt to describe real neural dynamics. You can basically say, I can predict the neural dynamics and vice versa from the belief updating scheme. And then you can sort of look at this both in space and time, where in the brain the lower level is, where in the brain the higher level is, what is more contextual and longer term, and what is faster and shorter term. And in the same sense, you can do that with the learning, the changes in the connectivity and the learning. We do that anecdotally using things like dynamic causal modeling to measure the effective connectivity as time progresses in, say, an EEG paradigm, and then ask, is that the kind of learning that we're seeing when we simulate the same paradigm in the computer?
Okay, so I think we'll end it there.